Okay, hello. Hello again. Hello, everyone. Welcome to the software testing 7 session. And my name is Apson Prapamuntripong. I will be your coordinator, your chair today. So let's start with the presentation. We have 6 presentations and we'll go by the order of the official schedule. And we'll bundle all of the talk at the at first, and then we'll follow by the panel session to do all the discussion. So let's start with the first paper. The first paper entitled A Family of Experiments on Test-Driven Development, presented by Zira. And this is a paper from the journal First Paper Track. And Zira, please feel free to share your screen.
Okay, can you see my screen? Thank you very much. So, test-driven development is an agile software development approach that has been widely claimed to improve software quality. The goal of this paper is to provide joint conclusions on the performance of TDD across different industrial and academic settings, and assess the extent to which the characteristics of the experiments affect the quality-related performance of TDD. For this purpose, we will conduct a family of 12 experiments on TDD in both academia and industry. Our research questions are: do TDD and iterative test last development perform similarly in terms of quality? Is quality affected by the task under development? Is quality affected by experimental design? Is quality affected by participants' characteristics? The main factor in our family of experiments is the development approach, being the treatments ITL and TDD. Both approaches consist of micro-iterative development cycles. In ITL, coding takes place before testing, while in TDD, testing takes place before coding. Our response variable is external quality, measured as the percentage of successful tests in the test set that we, the experimenters, have built. We will use 5 toy tasks, which are typical from other TDD experiments. The experiments in our family follow different designs, so they will vary according to the participant type being used, the design type, the environment, and the tasks. Our participants are more experienced with programming or the programming language than with unit testing or the testing tool used in the experiments. They have disparate experience levels and are absolute TDD novices. They don't have previous experience on TDD. For the analysis approach, we will use meta-analysis for research questions 1 and 3, and linear mixed models to answer research questions 2, 3, and 4. With respect to the first research question, we have found that participants achieve a slightly better quality with ITL than with TDD. However, the results vary largely across experiments. With respect to the task being used, we have found that it does not appear to be responsible for the difference in quality between TDD and ITL. As regards research question 3, we have found that different types of participants have show different scores for ITL and TDD. This is students and professionals behave differently with respect to the use of ITL and TDD. On the other hand, we have found that the programming environment and the learning effects are not having an influence in the results of the experiment, and the application order of treatments might have an effect, but this needs to be further studied in future experiments. Finally, as regards research question 4, we have found that in the case of professionals, more experience benefits ITL, while in the case of students, more programming-related experience tends to benefit TDD, and more testing-related experience tends to benefit ITL. So thank you very much.
All right. Thank you. This is very interesting.
Thank you very
And
much.
let's proceed to the second presentation, and then we'll hold the questions to the end. So the second paper that we would have today is about the impact of dormant defects on defect prediction, a study of 19 Apache projects presented by David A. So if you like to share the screen, please feel free.
Yes, can you hear me?
Yes.
All right. All right. Hello, everybody. I'm Davide Falessi from the University of Rome Tor Vergata, and today I'm going to present a paper entitled The Impact of Dormant Defects on Defect Prediction, a study of 19 Apache project. This is a 2000 paper at the Journal First of ICSE. So, a small introduction about sleeping and snoring. A dormant, also called a sleeping defect, is a defect that is not found yet in the release. So a class has a noise that we call snoring under two conditions. First, it contains at least one dormant defect, and second, it is labeled while all containing defects are still dormant. So now let's have an example so that we understand what is going on. Suppose that we have three classes and three releases, and due to time constraints, let's focus on classes 2 over 3 releases. So classes 2 in release 1, someone injects a defect in release 1. In release 2, nothing happens. And in release 3, someone fixed the defect that was injected in release 1. So when this happens, it means that only at release 3, we can know of this defect, because we cannot know of the injection without knowing the fix. So if this is true, what happens is that if we create a dataset and we label these classes in release 2, classes 2 will be non-defective in release 2 because we don't know about this injection. Whereas if we label those classes in release 1, classes 2 will be defective when we are in release 2. This means that the same class in the same release is labeled differently according to when the label is performed. So if this performance is 2, it is non-defective. It is performing in release 3, it is defective. This means that the labeling time impacts the presence of snoring. Okay. So the aim of this paper is to know and inhibit the negative impact of snoring on defect prediction. So we have two research questions. The first is, does snoring reduce defect prediction performance? And the second is, does defect prediction performance improve if we remove from the training set the classes that are labeled as non-defective in the last release? Now, due to time constraint, I'm going to present you the result only of research question 1. Before showing the result, let's look at how we designed the validation of research question 1. So first of all, we removed the last 0.5% of data because there might be snoring as well in our ground truth. So to avoid the presence of snoring in our data, we removed the last 0.5% of data. Second, we labeled the same exact data in 2 points of time. The first is after the training set. So when we usually need the data, then we label the data, right? The second is at the very end of the project, so maybe after 2 years. And this means that this data is without noise, is without snoring, and this data is with snoring. And then we compare the accuracy when the same model in the same project is trained with snoring versus the accuracy of the same model on the same project when it's trained without noise. And the result is that you can see here the loss across different data sets and different classifiers. And you can see that we lose in the median loss is about 50% in precision, but it's about 90% in recall. So the standard approach of labeling when we need the data and then use all the data leads to a reduction of 90% in terms of recall. And again, this reduction is only due to when the label is performed. It's not a different training set. It's the same training set. The only difference is when. So in conclusion, research question 1 results showed that the presence of snoring decreases the recall of defect prediction classifiers, while not significantly affecting precision. And so researchers shall consider neglecting the last half of data when validating prediction models. The second research questions showed that removing non-defective data from the last release significantly improved the classifier performance. And so practitioners shall consider removing from the training set the classes labeled as non-defective. Thanks a lot for your attention, and see you later for questions.
Thank you. This actually really opened my mind. I have never heard or have never learned about this concept, but it sounds really awesome. This is really interesting. All right, so let's proceed to the next paper. So the next one is about the RNN test towards adversarial testing for recurrent neural network systems, presented by Jin Min.
Hello everyone. I'm honored to be able to participate in the ICSE meeting. Today, the title of my presentation is Deep State, Selecting Test Suits to Enhance the Robustness of Recurrent Neural Networks. I am one of the authors of this paper, Zixi Liu. I am from Nanjing University in China. Below, I will officially start introducing our paper. In this paper, we proposed a test data selection tool for recurrent neural networks. As we all know, deep neural networks have been widely adopted in many fields, but there are still many errors in real-world application scenarios. In this work, we focus on the analysis of RNN, which is a special kind of DNN. With the RNN unfolded, each neuron in RNN's hidden layer updates its state and weight iteratively over time steps. Due to the differences in working nature and network structures between RNN and FNN, many existing criteria for FNN is not applicable for RNN. Now, let me summarize the challenges we are trying to solve. The first is why we need to select test data. Because the testing and optimization of RNN models rely on label data, and the cost of collecting and labeling data from real-world application scenarios is high. On the other hand, the existing test case selection techniques are rarely applicable for RNN models, and the analysis methods for RNN models are often aimed at advertiser sample detection, which may have limitations in real-world application scenarios. And this figure is an overall process of deep state. It first unflows the RNN model corresponding to the time steps and captures the predicted label sequence based on a stateful view. Then, deep state calculates the changing rate and the changing trend. These metrics are deployed to evaluate the uncertainty and the internal state transition of the RNN when processing the input data. Finally, we apply deep state to select a subset of the data from a large unlabeled dataset for RNN models. Now, let me show some experience in our paper. We experiment deep state with image classification and text classification models. For each data type, we employ two widely used datasets, and we apply some data mutation operators to simulation the data collected from real applications. And this is the bug detection rate of different selection methods. As can be seen, in each combination of dataset and model, the test set selected by deep state has the highest bug detection rate. And this is the bug detection rate of 10% and 20% selected tests. Similar to the results shown in the graph on the previous page, deep state has the highest bug detection rate for each selection ratio. In this page, the x-axis of each line chart represents the selection ratio from the candidate dataset, and the y-axis represents the inclusiveness of the selected dataset. With the selection ratio increasing, the inclusiveness of the test set selected by all methods is improved. Among them, deep state outperforms other selection methods, which indicates that deep state can select more bug test cases under the same selection proportion. In this slide, we show the RNN's accuracy score on test datasets after retraining with 50% selected tests. As can be seen from this table, in all models and datasets compared to random selecting data for retraining, the data selected by deep state can generally improve the accuracy of RNN models. That's all for my presentation, and thank you for your listening. Thank you.
All right, thank you, Xixin. And so let me get back to the title. So the next paper that we would be listening to is presented by Jianmin. It is entitled RNN Test Toward Adversarial Testing for Recurrent Neural Network Systems.
Hello, everybody. Could you hear me? Hello, everybody. I will introduce our TSU work for you. It's RNN test. As we all know, deep learning can be easily fooled, just like these adversarial examples. Thus, deep learning testing is quite challenging. As for existing test methods, they mainly focus on CNNs and image classification. However, there is a huge gap between CNNs and RNNs in model structures, tasks, and other aspects. And testing methods and coverage criteria for CNNs are hard to fit for RNNs. For RNN, it's a recurrent neural network. It's not a feed-forward structure. RNN models will iteratively make predictions given inputs. RNN includes three key components: hidden states, cell states, and gates. For different RNN models, they are of this similar structure, while only LSTM models have cell states. The difference of RNN model structures is the cell. LSTM and GRU cell includes multi-gates for keeping contact information and becomes mainstream RNN models. Now we show the workflow of RNN test. For original test input, the first step is to extract the hidden states and cell states of each RNN cell. These states are then used for the joint optimization. The first part purposely violates their inner dependencies of RNN tests to leading the model to give wrong predictions. The second part tries to cover more states to execute more decision logics. Then it will be solved in a gradient-based way to get perturbations. By applying two perturbations directly to original inputs, we can get adversarial inputs for models with continuous inputs like speech. For models with discrete inputs like text, the perturbations probably will not lead to a legal input, so we search along the perturbations and adopt the nearest one as the adversarial input. Finally, the input will be evaluated with model performance and coverage to help later testing. In this paper, we designed two novel metrics: hidden state coverage and cell state coverage. For hidden state, when to predict the next word following A, the hidden state units will be mapped to a least candidate. If a hidden state unit is the maximum, its mapped candidate will probably be the prediction result. So we define hidden state coverage to measure each hidden state unit whether it's for prediction. And also we have designed a cell state coverage to measure each cell state unit is whether it's for context preserving and in different degrees. For evaluations, we mainly select 4 RNN models, including 3 sequence-to-sequence models and 1 classification model. The first 3 of LSTM model and the mini GRU model is a GRU structure. And the final one is for comparisons to other RNN testing works. Over the testing models, RNN tests outperform FGSM and DLFAS with reducing the model performance more sharply and with higher success rate. For other RNN testing works, RNN tests achieve higher adversarial rate than test RNN. And for DeepStella, we also achieved more complexity and higher generation rate than DeepStella. Then we also found that coverage guidance could produce different perturbations with other methods. And state coverage guidance could generate adversarial inputs, outperform neuron-based coverage guidance, whether independently or joined with adversarial search. Finally, here are sample adversarial inputs over a model, a PTB model. Our adversarial inputs could result the model sampling was farther from semantics and generating higher perplexity texts. Here, final conclusions. You can check the paper for more results and welcome for more discussions via emails. Thank you very much.
Thank you for the wonderful talk. And let's proceed to the next paper. The next paper is entitled Evaluating and Improving Neural Program Smoothing-Based Fuzzing, presented by Mingyuan. And Mingyuan, if you like to share the screen.
Okay, can you see my screen now?
Yes.
Okay. So hello everyone. Today our presentation is about evaluating and improving neural program-based smooth-based fuzzing. And my name is Mingyuan Wu, and I am a PhD candidate under the University of Hong Kong and Sussex Joint PhD program, supervised by Professor Yuxin Zhang from Sussex and Professor He Chui from Hong Kong U. So overall, there are two existing fuzzers about neural program smooth-based fuzzing, Nils and Anyfuzz. Oh, I want to clarify that Nils and Anyfuzz also it is named as neural. It is actually targeting the binary fuzzing. So here's the framework of Nils and Anyfuzz. Under each iteration, they train neural network models using existing seeds from the C corpus by approximate the branching behavior of the target program. And note that the Nils and Anyfuzz adopt different neural network models. Nils adopt a single layer feed-forward network, while Anyfuzz adopt two additional tasks: the approach-sensitive edge coverage and the context-sensitive edge coverage, to construct the multitask neural network model for smoothing the program and further guiding the fuzzing. So after obtaining the neural network models, Nils and Anyfuzz randomly select a deterministic number of the seeds and explore edges. For each selected seed, they calculate the gradients of the selected edges vectors with respect to all the bytes. And Nils and Anyfuzz mutate the most promising byte by generating mutants or by shortening the gradient. Then we have mutants. Now, since Nils and Anyfuzz only adopted 10 popular real-world projects in their evaluation, we raised our first research questions. How do Nils and Anyfuzz perform on a large-scale dataset? Meanwhile, the effect of the key components in Nils and Anyfuzz, that is to say the gradient guidance, DLM models, mutation strategy, were not discussed about. So our second research question is, how do the key components of Nils and Anyfuzz affect edge exploration? And we have multiple important findings after evaluating Nils and Anyfuzz. So the first finding is the performance of Nils and Anyfuzz can be largely program dependent. So interestingly, such programs smooth-based fuzzers tend to perform better on larger programs. And the second finding is that randomly selecting bytes for mutation dominates the efficiency of edge exploration among all the studied fuzzing strategies, which indicating that it is promising to augment edge exploration by adopting random byte selection mechanism. And our third finding is that also the gradient guidance mechanism adopted by Nils and Anyfuzz are overall effective for identifying the promising bytes. Their performance can be rather unstable on some programs. And the fourth finding, personally, I think it is the most important one. That is, the different neural network models have limited impact on the effectiveness of program smooth-based fuzzing. So inspired by our findings, we propose Preventative, which is probabilistic resource efficient program smooth-based fuzzing, as our technical improvement. So here's the framework of our approach. Preventative first trains a neural network model by applying all the existing seeds as the training set. So next, the Preventative adopt a resource-efficient edge selection mechanism, which is designed for identifying the edge worth being explored to select edges for gradient computation. Then the gradient information is utilized to generate mutants for fuzzing. Meanwhile, Preventative adopt a probabilistic byte selection mechanism, that is to say PBS here, to facilitate the mutation. Then we also to generate a mutant. If such mutant explore a new coverage, it will be used to update the C corpus. And the evaluation results demonstrate that Preventative can significantly outperform the news by 47.1% and Defects by 45.2% in terms of edge coverage. So here is our conclusion. First, we have a data set including 28 real-world projects that can be used as a benchmarks for future research on fuzzing. And second, we conduct an extensive study of news and antifuzz on a large-scale benchmark shoot with detailed inspection of both their strengths and limitation. And we have a technical improvement Preventative, which combines a resource-efficient edge selection mechanism and a probability bias selection mechanism. And four, we also have some practical guidelines. The first one is simplicity neural network models may suffice. And second, we have to think twice before applying dynamic analysis. And next, the edge selection, yes, gradient computation, maybe we have to, we may have to switch our calculation on the fitness score for a single byte. And last, according to our finding, we suggest the users to design such probability search strategy with more guidance to any of their adoptive fuzzers when possible. Thank you. That will be all.
Thank you. This is really interesting. And let's proceed to the next paper. It is entitled Muffin, Testing Deep Learning Libraries with Neural Architecture Fuzzing, presented by Jiachen.
Okay, hello everyone. I'm Jiachen from Fudan University, and I will introduce our work, Muffin Testing Deep Learning Libraries via Neural Architecture Fuzzing. So let me introduce the background first. A deep learning system typically consists of three main parts: the source program, the library, and the infrastructure. And bugs can appear at any level of a DL system. And bugs in DL libraries may cause unexpected outputs of DL models. So in this paper, we focus on testing the DL libraries. And the previous DL library testing methods use either existing models or mutated ones as the test inputs. However, such models cannot cover most APIs in libraries. In addition, existing methods only detect the library bugs in the info. They mainly depend on detecting inconsistent model outputs from different libraries. And our target is to exercise more library functions and detect bugs in the model training phase. These two fields are not covered by existing methods. As a testing approach, there are two main challenges: how to obtain test cases and how to obtain test oracle. To tackle the challenge of test cases, we propose a DAG-based model generation algorithm to generate diverse models from scratch so as to cover the library APIs. For the challenge of test oracle, we propose a set of metrics based on data trace analysis that measures the inconsistency in model training. Based on these metrics, we can adopt differential testing to detect the training-related library bugs. This figure shows the overview of our approach, Muffin. It contains two main parts: the model generation part and the inconsistency detection part. In the model generation part, Muffin derives the model architecture from the structural information and layer information. It generates first generates the structure info and then generates the layer information. In the inconsistency detection part, Muffin detects the inconsistency in three different stages of model training: forward calculation, loss calculation, and backward calculation. In the model generation part, Muffin first generates the structure information, which describes how layers are connected. It adopts two model structure templates based on neural architecture search and uses a DAG to represent the structure information. Then, Muffin generates the layer information, describes the specific layer types. Combining the structure information and layer information, we can obtain model architecture. Finally, Muffin uses different libraries to generate deep learning models. And during the model generation phase, Muffin can detect crash bugs. In the inconsistency detection phase, machine participates the model training phase into 3 steps: forward calculation, loss calculation, and backward calculation. During each stage, machine detects the inconsistency in the library outputs and detects the crash bugs. During the difference measurement and inconsistency judgment, we use the chip-shift distance to eliminate the influence of different tensor shapes. And we use difference changes during 2 consecutive layers to mitigate the impact of floating point deviation. In the experiments, we testing 3 popular deep learning libraries, and our work detects 18 bugs in the latest version of 3 popular libraries, and it detects also 21 crash bugs. More details and the design can be found in our paper and GitHub repo. Thank you.
Thank you. Thank you for the wonderful talk. And we will proceed to the panel-like discussion. And I would like to invite the presenter to enable your camera and be ready to answer the questions. And to the audience, I like to encourage you to type your questions in the chat, or feel free to unmute yourself, raise your hand, and ask questions directly to the presenter. And I think there is one question already in the chat for Jian-Min, if you like to answer the question. And Ji-Yuan, would you like to ask the question yourself, or shall I read the question? Or maybe let Jian-Min read the questions and answer.
Thanks for the talk. So why did you choose the hidden state coverage to be the guidance of your testing approach? Is it just because you find more performance issues, or is it because of other reasons, hidden?
For hidden state, because hidden state is a key component in all RNN models, it makes predictions for RNN models, so we define coverage for that. We also, for LSTM models, we also design cell state coverage. It's just based on the functionality.
Thanks.
Oh, thank you.
Any other questions from the audience or from the presenter, if you like to ask the other presenter anything?
Can I ask a question about the deep state? Hi, Zixie. Other than no coverage, I think the Google has proposed TensorFlow in ICML 2019, and which it adopt activation layer value as the testing criteria. So my question is, have you evaluated in your experiment since the TensorFlow is another testing criteria other than no coverage? Maybe it is the related work for deep state. Yes, that's my question.
I think these states may be a little bit different from other neuron coverage criteria proposed in the earlier research. We focus on the hidden state, the transition of the hidden state vector of RNN, and we design 2 metrics to guide the test data selection, and we try to fix some questions, problems such as when you have a large scaled unlabeled data set, and you don't know you pick what data you need to pick and label this data for testing or optimization. So you can use the criteria proposed by deep state to help you select some valuable data for testing and optimization of RNN models.
Oh, okay, thank you. So actually the TensorFlow, it is using other testing criteria. It is using the activation layer value as the testing criteria other than no coverage. So maybe it is better to see the comparison in your paper's extension version. Yes, thank you for your answer.
Okay, okay, thank you. I would like to ask something about the RN test. It is excellent work and very inspiring to our work. And I would like to ask, what are the different application scenarios of hidden state coverage and cell state coverage?
Okay, it's a good question. Many people have asked this question. Because only LSTM models have cell states, so cell states can only be used for LSTM models and applications. And hidden state coverage could be used for all RNN models, including vanilla RNN models, LSTM models, and GRE models. But for the specific task, it may be not generalizing so well.
Oh, okay, thank you.
And I also have a question for Zixing. I see you have tried your deep state over LSTM GRU models. I think it could be of the vanilla LSTM or GRU. Have you tried on the larger models?
Not so far. We just tried the LSTM by LSTM GRU and the normal RNN models.
Okay, thank you.
All right, and we have.
Okay, I see the two questions for me, and I will just talk answer. Do not type. So the first question is, how do we measure the inconsistency for the training stage? Yes. The training stage typically have three main parts. The first, forward calculation is layer output, layer by layer, then calculate the loss value, and then use the loss value to backward layer by layer to upgrade the gradients. So our approach is collect the data trace layer by layer and compare the output variance of consecutive layers. If the difference from the previous layer are smaller than epsilon, and next layer the outputs the difference of outputs are larger than the threshold t, then I think then we think there is a potential bug in the corresponding layer, and in this way, since some layers, for example, the merging or the downpooling layers maybe reduce the variance, so we can detect more potential bugs in one model, potential layer bugs in one model. So that's for the first question, and the second question is about the main difference between Muffin and Lemon. There are two main differences. The model generation approach is totally different. Lemon just mutated the existing trained models. These models are public and do not need to train. And our work do not need these existing models. We just use our model generation algorithm to directly generate the models as test inputs from scratch, and can have a higher library API coverage. And in the training phase, because we do not have the reasonable model outputs, so we just use the layer outputs during the training. We collect the trace layer by layer and compare the difference to detect the inconsistency. And I also have one questions to Zixi and Jieming. Their work are all focused on testing deep neural networks. My question is, in my opinion, deep learning models are used to fit a specific distribution of the training data. So if you generate a if the adversarial input or other test input your approach found is different from the original training data, the distribution are different. Do you think this is what do you think this kind of testing is reasonable or not? Just if the test case your approach found has a different distribution from the original training data, because there are some paper talk about the different distribution may cause the model have some problem.
Maybe I could not answer this question because we haven't experimented on that. Sorry.
I'm interested in the problem of data distribution, and we found that there are recently some researchers talking about data distribution, and we agree that if a test distribution, if the test data the model is not and retrain the model to fix the distribution problem. That's all.
Looks like her internet connection is not very good at the moment.
Yes,
Is
we
everyone
can ask more questions through email. I think there is a network problem. Yeah.
Okay.
Any other questions from the audience or from the presenter or the author?
I still have one question. Can I? Yes. Hi, Jiazhen. If I'm not confused myself, you are using the generation-based strategy to generate your test case, right? So my question is, what is the reason that you not trying to use the mutation-based strategy to generate your test case? Because we know that mutation-based strategy you can just do a little change to the original seed, then you have a new test cases. So why you use the generation-based strategy instead of mutation strategy? Yes, is that means because some model is really hard to retrieve, or the test cases is not available in most of the time, so we have to use the generation-based strategy.
So our layers input, the tensor shape has restriction. You can, if you mutate the existing model, the mutation has to be a little, and you cannot achieve higher coverage of the library APIs, because some APIs may be just not used by existing models. And our main idea is that our target is to testing the libraries. So we do not care about the model performance, because existing models are designed to achieve higher performance with specific data sets. But our target is to find the bugs from the implementation of the library functions. So we just generate models from scratch, and we can comprehensively exercise the library codes.
Okay, so since there is some constraint on the model, so if we generate from the scratch, it will be much easier than mutation on the existing model, because the mutation cannot all have more difficulty in following the constraint. Do I get your meaning right?
You need to collect and
Thank you, thank you. I think we can communicate by email or something that. Thank you. Anyway.
Well, sounds like his internet also is not doing well now. If everyone is okay, may I also ask a few questions? I have a question for Sarah. You talk about a series of experiments using TDD, and I am wondering. Oh wait, hold on. Where's Sarah? Okay, and I am wondering if during your experiment, did the participant participate individually, or has it been done in groups? How big the group? Individual?
No, they were working individually. The task was being done individually.
And so you suggest that you allow them to use multiple languages. Is there any specific kind of application to build? Any specific domain? Is it a standalone, a web application, mobile application, or any particular kind of application?
Okay, so they were using, with respect to the programming languages, they use, in some experiments, they use Java. In others, they use C++, and there was, I think, one more experiment in which C# was used. And with respect to the programs, we have reused programs that were used in, they are well known in the TDD community, and they are typically used in previous experiments in TDD, or either they are well known in the TDD literatures. Like, for example, there's this bowling score keeper, which computes the scoring in a bowling game. And there's another one for listening. It's it's music phone, and it's about an interface for listening to music. So it allows you to create playlists and all that. There was one more, which was called a Spreadsheet, and it simulates the behavior of a spreadsheet. So they were more or less different from different domains. So functionality was quite diverse. But the main thing is that they had in common that they were small tasks. So they were not like big programs, because it was not possible for the experiment. So we needed the experiment to be done the coding task had to be done like in 2 hours, 2 hours and a half, something like that. So it had to be a small task.
Would you be able to share the material? I'm interested in trying this in my class. I have also doing a series of TDD.
Yes,
okay.
In fact, since this is a journal paper, if you go to the paper itself, there's the GitHub repository where everything is in. But I mean, in case there's something missing there, if you need something or want to check something, just let me know, and I will be very happy to send you any material you may want.
Awesome. I would love to. I would love to learn more about this experiment and a series of TDD. I use TDD in my class, build a standalone and then a web app. But that would be interesting to enlarge the scale of the software. This is wonderful.
Yes.
Okay. And if I could ask, I also have another questions for Davide. This is the sleeping and snoring are really interesting, and this is the first time that I have heard of these terms. But it sounds like it could somehow be very useful when we apply to test automation, would it?
Yes. What specific type of test automation? What
Like,
do you refer to as test automation specifically?
I have seen a lot of problems in test automation when sometimes we have blind test, fuzzy test, or some test that's not going to reveal anything. But based on your explanation, you mentioned about when it's detected. It's after some time, depending on when we label, it's going to change whether it's detect or non-detect. And that's just
Yes.
give me an impression that it could probably be very helpful with test automation to improve the quality of how we decide test.
We will have to check. I mean, the bug is already there. So if you apply test, you will likely find the bug at the first release. So the bug will not slip, and so it will not impact the test automation. The problem is that if you don't find the bug, and then you ask yourself whether the class is with a defect or not, then you believe it's without a defect. And everything started before because when we developed the datasets to perform our prediction studies, the last releases were always without bugs. And so every project had the last release without bugs. And so that, yeah, we asked ourselves why. And because this file has bugs that still have to be found. And so this is where we start from.
And then you mentioned about when to label. How do we know
Yes.
when would be a good time? How can we determine?
Yes, we have another paper, I think was published at MSR 2020 or something like this. And it's about how many classes somehow you mislabel when you wait a specific amount of time. And I think data shows that if you label at the end of the project, and then the first half of the project is pretty reliable, so you miss about 1% of the data. So it's something that you can live with. But yeah, so we have a paper that is referenced in the paper I presented, where we have a specific combination of how much data you shall waste or wait, and how much is the noise that you will get. Of course, the more you wait, the less the noise.
But then, yeah, well,
Yes.
please go ahead.
So, yeah. So when we label, we don't perform tests. We just see the result of other tests. And so the idea is that if you don't wait for others to perform tests, then you cannot label the classes as defective or not defective. And so the more you wait, the more the tests you have, and the better the label is.
But then sometimes we don't really want to wait, right? We want to find problems as early as possible.
Yes, there are two different scenarios here. I think there is a scenario where you want to test, and hopefully you don't need a defect prediction because you can test, I don't want to say everything, but at least most of the code. But there is another scenario when we want to test our defect prediction models, for instance, and we want to understand which one is more accurate and whether a new feature is important, or, you know, we do a lot of research on defect prediction, and we rely on the data set. And the data set is used as a training set for the model. And now if the training set is not accurate, then we have the problem of garbage in, garbage out. And so the results are not reliable. So on one side, we should not wait for testing. On another side, if we use data as an input of a defect prediction model, then this data needs to be accurate. And the last releases are inaccurate for what concerns the labels of the classes.
This sounds very interesting. I have to read the paper that you just mentioned. I'm interested in knowing when would be the best return on investment. We want to wait, but not too long, but then not too soon. Thank you.
You're welcome.
Any other questions from the audience? Or from the presenter?
And I have a question for Mingyan. I see that you have finding the simple neural network may suffice. I'm interested in how you find that.
Oh,
Thank
yes. We have tried multiple models to try to approaching the target programs branching behaviors. And the most interesting is that all the models, no matter you try by CNN, IN, or by LSTM or something like that, or transformation, the results are similar. Actually, the largest performance gap is CNN, which can outperform the existing state of the art by only 3.3%. So we investigate the reason behind the scene. The reason is because if we try to switching or explore a new branching behavior, we have to remember so the existing input, the existing seeds, and which byte is critical. Which byte is critical to existing branching behavior. So as a result, the model here is using to remember. It's using to remember the historical data. We want to retrieve the existing information from the historical data. So actually, there's no prediction here. There's no prediction here. So because there's no prediction here, so actually the fancy models are actually doing the same job as the simplest model, which is feed-forward network. So all things is to remember. As a result, the simplest model can suffice. Yes.
Okay, thank you very much.
You're welcome.
Any other questions from the audience or the presenter? Well, if not, I think we could call it a day. And thank you, everyone. Thank you, the presenter, for the awesome presentation. I have learned many new things. And now I know what papers I'm going to make my students read next semester when I do a software testing class. So thank you, everyone. Thank you for an awesome presentation. And thank you, everyone, for attending the talk. Thank you.
Thank you.
Have a good day.
Thank you.
Thank you.
Thank you. Thank you for sharing.
Thank you so much.
Thanks.